particle oscillates between two extreme positions about the mean position. This is called as linear, simple, harmonic motion or linear etc. Here in this case, as we know, the restoring force acting on the body is in opposite direction to that of the displacement. Restoring force F is equal to minus kx. Minus sign indicates always the displacement and force will be in opposite direction. If the particle crosses and comes to the left, the restoring force is toward the mean position acting toward the right when the displacement is toward the left. On the right hand side, the displacement is toward the right hand side, the force is acting toward the left toward the mean position. So always the restoring force will be acting toward the mean position. And so here we see that the restoring force F in simple harmonic motion will be equal to minus kx, where minus sign indicates that force and displacement are in opposite direction. In terms of magnitude, F is equal to kx. K is the constant of proportionality. It is also called as force constant. K is force constant. Or we can give the value of K as F upon X. So it is force per unit displacement. Force per unit displacement. We know the force is always expressed in terms of Newton. SI unit of force is Newton. And displacement is having its SI unit as meter. And so K will be Newton per meter. It is force constant. Yes. Or force per unit displacement. We also know force can be expressed as mass into acceleration. M is the mass of any of the object on which this restoring force is acting. As in terms of magnitude, F is equal to kx so K upon M into x will be the acceleration. So this is the force constant, which is a constant term, mass is a constant term, and so we can say that acceleration in case of the simple harmonic motion is directly proportional to the displacement. In terms of direction, acceleration will always be in opposite direction to that of the displacement. As we see, the force is acting toward the left hand direction, the acceleration will be left hand directed when the displacement is right hand directed. When the force is acting toward the right, the acceleration will be toward the right when the displacement is toward the left. And so in simple harmonic motion, always the displacement in the particle will be in opposite direction to the restoring force and to that of the acceleration produced due to the restoring force. Now, as we are discussing about this, We'll study this in detail, but since this is the mean position and let these to be the extreme positions, we see that at the mean position, the restoring force F is equal to 0 when the displacement is 0. So x is equal to 0, F is equal to 0. When object moves to the extreme position over here, we see that F is maximum when x is maximum. The restoring force will have its magnitude maximum when the displacement is maximum, though their directions are opposite. Particle stops over here for a moment. Because if it doesn't stop over here at B, then it will keep on going toward the right continuously. So for the simple harmonic motion to be in effect, the object has to stop at extreme position. And as the object stops over here, its velocity becomes equal to 0. So when object reaches the extreme position, its linear velocity becomes 0. And now, as the velocity is 0 and the force is acting toward the restoring position, the particle starts moving. Its displacement, its distance with respect to the mean position goes on decreasing. As x goes on decreasing, the restoring force also goes on decreasing. But at that time, the velocity goes on increasing. And so when the particle reaches its mean position, V is maximum. As force becomes 0, x becomes 0, acceleration is also 0. Now the particle crosses the mean position, so the velocity goes on decreasing because the object starts becoming slowed down and the velocity will become 0 at the extremity when force and displacement are maximum, and again the process will repeat. And so from this particular figure, in nutshell, we can say that the linear velocity in linear simple harmonic motion is 0 at the extremity, it is maximum at the mean position. Restoring force, the magnitude is maximum at the extreme positions, direction is toward the mean position, the displacement is maximum at the extreme position. This maximum displacement of the particle performing linear simple harmonic motion is called its amplitude. Usually we will denote it by A. So in case of the simple harmonic motion, A is the amplitude. Whether the motion is in vertical direction or in horizontal direction, whatever it may be, the maximum distance which has been covered by the particle from the mean position toward the extreme position will be called its amplitude. It is measured in terms of meter. As SI unit, symbol is M. For the smaller magnitudes, we can measure it as centimeter or millimeter, but its SI unit will be meter. And so we define the maximum displacement in simple harmonic motion as its amplitude. Now, when we see this particular motion, it begins with the mean position, say O, particle goes to one of its extremity, stops here momentarily and return back to its mean position, goes to another extremity, stops here momentarily and return back to its mean position. So the motion starting from mean position, going to one of its extremity, returning to the mean position, going to another extremity and returning back to the mean position for the same state of vibration. See, the same state of vibration. The vibration started, particle moving toward the right. When it returned back, it is in the way it is moving in opposite direction, and now it comes to the same state of vibration as the beginning. This completes its one vibration, or it completes its one oscillation. Now, the time required to complete this one vibration or one oscillation is called its period. Period of oscillation or period of vibration. It is denoted by capital T. SI unit is second. Yes. Number of such vibrations performed in 1 second. Number of vibrations or number of oscillations performed in 1 second is called its frequency. We can denote it by F or we can denote it by eta. So frequency F is the reciprocal of period. So we can measure this as per second or hertz, H is it. So in case of simple harmonic motion, the maximum distance covered by the particle to either of the extremity is called its amplitude. Time taken by the particle to complete one oscillation is its period, and number of oscillations or number of vibrations it performed in 1 second is called its frequency. So when we are going to derive the expressions for oscillatory motion or simple harmonic motion, these definitions are going to be very important definitions. Yes. Now we will study a very important part of this particular topic, that is the differential equation of simple harmonic motion. Before, from the textbook, we'll once read out the definition of linear simple harmonic motion. Linear simple harmonic motion is defined as the linear periodic motion of a body in which force or an acceleration is always directed towards the mean position and its magnitude is proportional to the displacement from the mean position. So this is the definition of linear simple harmonic motion. Now let us discuss about the differential equation SHM. Yes. Differential equation of SHM. Consider particle performing linear simple harmonic motion along the path AB above the mean position O. Let small a be the amplitude of this particular linear SHM. Means the distance of its extreme position from the mean position is small a. As the particle gets displaced from the mean position, so for the distance x, then the force acts on the particle. As the force is a restoring force, it will be directed toward the center when the displacement is away from the mean position. Particle is moving towards B. In this case then, we know that force F is directly proportional to displacement x. Therefore, F is equal to minus kx. Minus negative sign indicate that force and displacement are in opposite direction. K is force constant. Now, what is force? Force is nothing but the product of mass of particle and acceleration in the particle. This will be equal to minus kx. Now, what we know about the acceleration? Yes. If x is the displacement, then velocity in particle V is equal to a rate of change of displacement. A rate of change of displacement is velocity. And what is a rate of change of velocity is? Acceleration is a rate of change of velocity, that is dv upon dt, which will be d of dt of dx upon dt. Now, from this expression, what we can write about acceleration is rate of change of velocity, means it is the double derivative or a derivative of derivative. So you can write it as second order derivative d2x upon dt2. Mind well, this is not a square of dx by dt, it is the second order derivative. It is the derivative of derivative. And so over here, acceleration can be expressed as d2x upon dt2. Velocity v can be expressed as dx upon dt. And so, in the given expression, for the force acting on the particle performing simple harmonic motion, we can write this as m into acceleration will be d2x upon dt2. This will be equal to minus k x, or we can express this as m d2x upon dt2 plus kx is equal to 0. If we divide the entire expression by m, we can write this as d2x upon dt2 plus k upon m x. This is equal to 0. This is called as the differential equation of simple harmonic motion. We also know that as omega square is equal to k upon m. Yes. This expression I will explain you when we will be equating the simple harmonic motion to the circular motion. At that time we will be defining how the angular velocity is related to k upon m, but right now we will see omega square can be expressed as k upon m. So expression d2x upon dt2 plus omega square x is equal to 0 is the differential equation of simple harmonic motion.